Okay, off we go. So, last time, here's where we were. We were talking about this new idea called a scalar line integral. Kind of a weird idea. The big issue is sometimes our domain is what I like to call dimensionally weird. Right? It's the wrong dimension for the world that it lives in. And so a nice example is a curve. Right? A curve is an intrinsically one-dimensional thing, but it's living in a two-dimensional space. So it's not, I can't use a double integral. I can't really directly use a single variable integral. Y'all okay? Okay. So it's dimensionally weird. I'm not clear what to do about this. So we invent a new kind of a Riemann sum, and the Riemann sum is this right here. Okay. Same strategy with every other kind of Riemann sum we've ever thought of. We take our domain, we chop it up into little pieces. Right? That's the natural thing to do. Chop it up into little pieces. And the idea is if we have a quantity, not every quantity has this property, but if the quantity has the feature that the whole is the sum of the parts, I can just look at the parts individually. I can look at one little part. I can ask what's going on, what am I interested in on that little piece of the domain alone, right? And then add up over all of those little pieces. Okay. All right, so this is about where we left off last time. I guess I made a reference to this notation and this term. Let me say that again, but this notation is just like every other notation we've ever seen for an integral. The subscript indicates what the domain is. The integral symbol represents that we're adding things up. It's just like all other integrals. And the term scalar line integral, this term line integral is a reference to the fact that the domain is a curve. In other contexts, in other eras, right, the term line can be taken to mean a curve. That's the intention here. Scalar, because the integrand is a scalar. Seems like a weird observation to make. The great majority of integrals that we've ever seen so far, the integrand was a scalar. We're going to see later today a different kind of integral where the integrand is a vector. And even weirder, here the differential is a scalar, and we're going to see an integral later today where the differential even will be a vector. It's just a strange kind of a thing. But that'll come up in context, so more on that later. Okay, big question then, how do I compute these things? How do I compute a scalar line integral? I'm going to point out we're in a situation much like when we were doing change of variables. We have a domain we don't like. Now, why we don't like this domain? It's a different reason that we don't like it. It's not because of corners. It's because it's dimensionally weird. Right? But when you have a domain you don't like, we can still kind of steal the same strategy we used previously. View it as being an image. Once you view it as being an image, then you can pull back the integral and get a new integral on your pullback domain. So the good news is how to view this as being an image is something we know from long ago. Back in chapter 1, we talked about parametrizing curves. And if you think about it, that's exactly what a parametrization is. A parametrization is a way of viewing your curve as being the image by way of some function of an interval on the t-axis. So just like with change of variables, I'm going to say, look, this original integral that we had, wrong color. This original integral that we had, I'm going to do the pullback to rewrite that as an integral now on my pullback domain. It's mostly a matter of plugging in. And the only one little micro detail that we have to deal with is what is that stretching factor? How much does a little piece, let's see here, let's just get rid of all that. If I have a little piece of the t-axis and its image is a little piece of our curve, and if I want to know by what factor does that get stretched out to make that, just remind ourselves, a pretty convenient way to think about parameterizations is or parametric curves anyway, is that the parameter is time. If your parameter is time, this says in some little amount of time, and this says what is the corresponding amount of distance that we cover in that amount of time. And the relationship between distance and time is speed. Right, this is a convenient sort of physical realization. That stretching factor is speed, because speed is what you multiply by time to get colors, to get distance. What do you think? Everybody buy it? Okay, so this is how our pullback strategy works, and frankly, it kind of works even better than change of variables did. Change of variables turned an ugly, like say, double or triple integral into a better double or triple integral. Here, we turned it into a single variable integral. Calc 1 style, single variable integral. This is highly computable. It's just again, Calc 1, Calc 2 methods. All right. Now, there is a concern here. You might be weirded out by this concern. I'm going to address this pretty quickly. What we're interested in, reminder, is something that, we're looking at a curve. We're looking at some function defined on this curve for whatever reason appropriate to the whatever the application is we're trying to apply this construction to. We've got some integral. And the curve exists completely independent of any parameterization. There is no parameterization when we encounter this problem in the first place. There's just a curve. It's just sitting there, right? And we're saying that the answer is going to be computed by an expression that clearly seems to depend on how you parameterize it. Worrisome. Right? Something that does not depend on the parameterization. Why does my expression require a parameterization? What if you parameterized it one way, you parameterized it a different way? What if you all get different answers because you use different parameterizations? Seems kind of plausible. There's the parameterization right there. It might matter. And the good thing is that it doesn't. So the value you will get is independent of the parameterization. Parameterize however you like. It's got to be continuously differentiable, otherwise we can't. The integrals aren't defined anymore. But aside from that, whatever you want to do, don't worry about it. Okay. All right. Let's do one. We have an irregular wire. So most wires are pretty regular. Any little piece of the wire looks like any other little piece of the wire. Mass per unit length is usually constant. So what I'm saying here is we have a weird wire where there's more mass per unit length in some places than in others. Okay. This wire is following a certain curve. The curve is parameterized like so. By the way, real quick aside, I'm giving us the parameterization so that we don't have to be distracted by how do we parameterize. Remember, we spent a lot of time discussing parameterization. And notice this one, you can even see what curve this is. This is y equals x squared. Right? So something to think about. Make sure you're comfortable with that. So that's the curve, and here's how density, here's the mass per unit length, how that is distributed across the curve. And I want to compute the mass. Well, I also want to compute several other things. I want to know where's the center of mass. That's both an x-coordinate and a y-coordinate. And I also want to compute the moment of inertia, let's say around the x-axis, whatever. So we're going to do 4 separate calculations here. And one of the big takeaways is how much these calculations are going to have in common with each other. They look like completely different calculations, but all of these questions involve the same wire, which follows the same curve, which is parameterized by the same function with the same density. That parameterization, of course, has the same derivative and therefore the same speed and therefore the same stretching factor. All of that exactly the same for all 4 of these calculations. So something to keep in mind, right? Once you've done one calculation, one scalar line integral on a given curve, you're kind of set up to do a bunch of them already. So nice little benefit. You'll see how that pays off in a couple of minutes. Let's write down the computation for mass. As y'all recall, I like to start off with this. This is my little acknowledgement that mass is an accumulating quantity. The whole is the sum of the parts. Right, so we can apply the idea of an integral because it has that feature. Mass is density times size. In this case, mass is mass per unit length times length, because the mass is distributed per unit length across this wire. All right, let's see here. We know from the previous page that ds is speed times dt. We just got through computing that stretching factor speed is that. So you plug that in. We were given in the statement of the question, I guess I got to zoom back out. We were given in the statement of the question that density is x plus y. So notice it's just mostly a matter of plugging in. Right? The one thing that my experience has been that students have a lot of trouble with is figuring out what in the world to do with, for example, x. Right? What's the deal with x? The answer to that question comes from the previous page. Remember, the variables x and y here that you start with, those are the outputs from whatever function it is you're pulling back through. So you remember when we were doing change of variables, you pull back through what was a change of variables function, and the change of variables function explicitly tells you x and y as functions of whatever your pullback parameters are. Here, we're pulling back through the parameterization. So x, in this case, it's the first output from your parameterization. And check it out. That's explicitly the case here. X, there it is. X is t, given in the parameterization. So that's what we do with x. X is t. Plug that right in. What do you think? Everybody all right with that? Cool. Okay. Likewise with y, of course, you'll notice y is t squared, and so like so. All right. Now, let's look at this next one. Let's look at how to do x bar, and this is where things are going to get really efficient. We write down the formula for x bar. You got to start with that. You'll notice we've already computed m, or at least we've already written down an integral to compute m, so that's fine. And then notice this. We've got a dm right there. Same dm that we had here. That dm, we've already gone to the trouble of rewriting that dm. And all of that comes along for the ride. It's the same development there. We don't have to do that all over again. We just kind of copy from what we did before. Everybody happy with that? Nice little time saver. You don't have to reinvent the wheel when you've already got it. So the only extra thing, of course, you look at the integral that we're dealing with. Get this to cooperate. There, I better stop there. The only extra thing to deal with is that x, which carries through, and again, x is t. How are we doing? Is everybody okay with that? Any questions? Feel free. Okay. All right, pretty plug and chug. Take a look at these last two examples. It's more of the same. You're going to notice, again, a lot of freebies, right? But just ever so slightly different and something to pay attention to. Okay, next question. We're going to consider a different scenario. Here we have the unit circle. Here's a portion of that unit circle just for visual convenience. And we have a fence sitting on top of the unit circle. So, for whatever reason, I've got a plot of land here, and I want to put a fence around that land. The weird thing about it is the height of the fence is not going to be constant. For some reason, I want the height to be greater over here and lower over here. Now, why would I ever do such a thing? Here's a plausible scenario. Maybe my land isn't flat. Maybe my land is tilted, right? And, well, I need a taller fence on the sort of the bottom side, because otherwise the people that live on the next hill over would have line of sight into my house, right? So I need a taller fence for privacy there. I need much less of a fence on the other side because the hill is giving me the privacy for me. Does that make sense? Kind of reasonable? So, weird fence, but set up as I have it here, I'd like to know what's the area of that fence. Why would you need to know the area of the fence? Maybe you're going to hire somebody to stain your fence, and that's a non-trivial expense, and he's going to charge you by the square foot, and you want to make sure to check that arithmetic, make sure you don't get overcharged. By the way, I do little stuff like this in my own sort of personal life. I check the arithmetic on various things, and wouldn't you know it, I have caught people trying to overcharge me several times, and I've saved myself thousands of dollars by just checking the math on a few things. So it's something to think about, and this is, for your how you conduct your personal matters, it's up to you. But I like to double check things and save money. Okay, so first argument I will make is that the whole is the sum of the parts. If I break up this fence into pickets, kind of picket-like little pieces, little slices, the total area is the sum of the areas of the pickets, right? Okay. All right, so let's look at one little picket at a time then. What's the area of this? I'll try to keep the thing in. Okay, good enough. What is the area of that thing? Well, I claim the area pretty immediately. Oh, whoops, I didn't mean to. The area is going to be the height, which we're given, times the width. And if you think about it, that width is a little piece of the curve that my fence is sitting on. This is ds. When I take my curve and chop my curve up into little pieces, this width is one of those little pieces. And so that width, ds. What do you think? Height times width gives me area? Yeah? Okay, and check it out. We have ourselves a scalar line integral here. And so now we just need to compute this scalar line integral, and we've got the formula. The big idea is you just plug in one little bit at a time. Our ds, let's see, I think I used red for this. ds is stretching factor times dt. We better compute that stretching factor. How are we going to compute our stretching factor? Let me remind you, come back to here. The stretching factor, here we go. The stretching factor is the derivative of my parameterization, specifically the magnitude of the derivative of the parameterization. This curve did not come pre-parameterized. It just says the curve is the unit circle. So here we're going to have to actually do the parameterizing. And good news, parameterizing the unit circle is pretty straightforward. In fact, this is the very first parameterization we ever wrote down back in section 1 point something, right, long ago. Hope y'all remember this one. By the way, this is, I don't know if you remember, but when we first started talking about parameterizations, I made the observation, we're going to be using parameterizations a lot when we get to chapters 6 and 7. Here we are. Right, so this would be a pretty good time to go back and remind yourself, kind of refresh yourself of all those different methods for how to parameterize curves. Here's where we're going to be doing a lot of it. Okay. All right, so we parameterize. We take the derivative, we take the magnitude, and you see our stretching factor, our speed is 1. Everybody good so far? All right. Let's see, the next thing, we've got to plug in for the height. Well, the height we were given was that formula. Here's the same question we faced previously again. And that is, what do I do with this x? Right, well, remember x, you can see it right there. X is one of the outputs from your parameterization. And here it is specifically. X is cosine t. And we just plug that in. Like so. Everybody with me? Everybody happy? Okay, and then single variable calculus. Y'all can do that. Okay. All right. So let's see here. Moving along. Another seeming example. Now I got to be careful how I say this. This is an example where, at a quick glance, it feels like this is going to work. It feels like this is going to fit our mold of our scalar line integral, and we're going to proceed with an open mind as if this is going to work, and then we're going to start to get some raised eyebrows at a couple of things that we're going to notice are qualitatively different, and we're going to end up kind of thinking of this in a different way. But at a quick glance, it seems like scalar line integral ought to do it. So let's just go ahead, see what happens. This is going to be about computing work. Y'all remember work from, again, chapter 1, right? And we don't, the high school take on work is that force and displacement are scalars, and you multiply them, except you have to account for the fact that they go in different directions, and you have to look at the component of the one, and they have all this verbiage, right? And we saw in chapter 1 that the much better way to think about this is just to recognize that force and displacement simply aren't scalars. They are vectors. They have direction, right? Force has a direction. Displacement has a direction. They're vectors. We write them as vectors, and amazingly, conveniently, the dot product perfectly accounts for all of that asterisk of, well, you got to look at the component of the force and the direction of the displacement and all that stuff. The dot product handles that for us. Okay. All right. However much of an improvement this formula is, it's still not really quite good enough to handle a general scenario, because this assumes the force is constant, which it might not be. And it assumes that the displacement is over a straight line path, which it might not be. In fact, it usually is not a constant force. It's usually not a straight path. All right. So here's what we're going to deal with. Suppose we have, I've already forgotten what colors I just used. Suppose we have a path that is not straight. And suppose we have a force that is not constant. How much work does it take to do that? I like to think, by the way, just my metaphor, what I like to visualize while I'm thinking about this is that this purple curved path is a windy mountain road. We're driving from, where the interstate is. We're driving up this windy mountain road to get to the top of whatever. Okay. Here's where we try to do this with a scalar line integral and start to run into problems. Very first thing we would do with a scalar line integral is say, okay, let's break this up into little pieces. Let's look at that one little piece by itself. Right, that one little piece. Notice that piece is approximately straight. Not exactly, but pretty close. In the limit, that is effectively straight. The force over such a small distance doesn't have much chance to change. The force is approximately constant. It's feeling pretty good here that we should be able to write this down with a scalar line integral. Everything's lining up so far. But here's the problem. I have to recognize that I'm going that way on the curve. It's what we call an orientation. I'm not just driving this road whichever direction I feel like. I'm going uphill. The question is, how much work does it take to go uphill? Specifically uphill. We have not seen that feature in any of the previous examples that we've looked at. This fence, I don't really care which direction you stain it. I don't care. There kind of is no direction of the stain. The area just is. There is no sort of, well, there's a this direction area and a that direction. It's not. It's just the area. It just sits there. Right? So there is no notion of orientation that factors into this question at all. And likewise, for all of these examples here, mass, location of the center of mass, it just sits there. There is no notion of direction. So this is something's different. Something is not the same here, and our scalar line integral construction doesn't seem to recognize this important distinction. Does that make sense to everybody? I hope. Here's another thing. It's actually worse than this, because even the direction that the road is arranged, the fact that it's kind of that way, independent of the question of, am I going this way or that way? The fact that I'm going in that direction matters, right? Because, for example, like so, you can tell that this line is kind of, well, yeah, there's a sort of an uphillness to it. You can see the direction of uphill is like that, and this is somewhat uphill. The fact that that little piece of road is arranged that way as opposed to that way. Right? If the road were like this, there wouldn't be any uphill or downhill at all in either direction. We don't have anything like that with the fence. Right? With the fence, I just need to know the width. And it doesn't matter if this particular little picket, if this picket, imagine my phone is a picket here, doesn't matter if that picket is like this or like that or like this, kind of whatever. Right? So there's a lot going on here about directions that is not recognized by how scalar line integrals are set up. All right. Okay. All right. So at this point, I think we'd be well advised not to try to turn the answer to this question into a scalar line integral. I don't think the scalar line integral is the right construction. It doesn't recognize some very important aspects of this question. So here's what we're going to do. We're just going to kind of write some stuff down, see what happens, and it turns out we get something pretty directly. Here we go. On a piece of curve, such as that, if you want to know how much work does it take to move along that piece of curve going the direction we're supposed to be going, well, there's a displacement, dr. There's the vector field, recognizing the force that I apply as I go along that displacement. That force is F. And on that little piece of curve, dw is F dot dr. And recognizing that work also has, whole of the sum of the parts, plug in dw equals F dot dr. We have a new kind of an integral here. This is a line integral. Oh, let's see here, color choices. We have a line integral because, again, we're adding up over an entire curve. So the term line integral makes sense, but it's really a different kind of a critter. This is a vector integrand But worse than that, creepier than that, we have a vector differential. We have never seen that before. We've seen the dr vector before. That's just kind of an independent thing, but we've never seen the dr vector as the differential for an integral before. But it fits perfectly here. Is everybody okay with that? All right, so this is called a vector line integral. This is the term that Colley uses. I like this term quite a bit myself. I use the same term. Not everybody does. FYI, sort of a heads up, a lot of people just call this a line integral. And it's a line integral set up to solve this kind of a question, and that's reasonable too. I like making the distinction just to emphasize that there is something more going on here that scalar line integrals kind of don't really quite recognize. Okay. All right. How to compute these things. Flashback to chapter 3. And you may recall we talked about parametrizing curves and derivatives of parametric curves, and we wrote down a bunch of stuff about r prime and the dr vector and the ds scalar and the unit tangent vector capital T, all this stuff. This is sort of the top of the first page of the lecture notes for section 3.2. Remind yourself of all of that. We said at the time this is going to be really useful in chapter 6. Here we are. So make sure you're good with all of this. In particular, these relationships right here. Very important. And this gives us exactly what we need, frankly. We're looking at a vector line integral. And we have these various different ways of representing dr. And notice, one at a time, if you plug in these different takes on what dr is, you get different alternative ways to write vector line integrals. So all three of these expressions down here, these are all saying the same thing, really, kind of, just with sort of different notations, different written in terms of different players related to the parameterization. How are we doing? Does that seem reasonable? All right. Okay, all three of these are good. I like all three of these expressions for different reasons. This is my favorite one. Several reasons I really like this notation. For one thing, it's the shortest, right? It uses the least amount of ink, right? So that's kind of nice. I got to count for something. Not the main reason I like it. My biggest reason that I like it is that this dr encapsulates everything that we need to know about our little piece of curve. That dr tells us how long that piece of curve is. It tells us what ds is, because ds is the magnitude of this vector. So the ds is hidden inside of this vector. We also need to know, we talked about this, that I need to know if that little piece of curve is pointing that way or this way or that way. I mean, how is this arranged in space? dr tells me that, because dr is literally pointing in the direction that curve is going. So everything that you need to know about the little piece of curve, everything that you need to know from this integral about this piece of the domain is represented in that one thing, dr. And then by contrast, the f, everything in the integral that is not intrinsic to the curve is in that integrand. Right? So f, the vector, the forces that are being applied, the forces that I'm having to exert as I move along the curve, those are independent of the curve. All of that is in the integrand. And I think, from an organization standpoint, I think it's really nice to keep these separated. Here's the curve stuff. Here's the not curve stuff. It's just organized. Okay. All right, so I like it for that reason. Now, I think there's a pretty clear, obvious reason why I like this one. This one is plug and chug, right? If you need to turn the crank and get an answer, right? If you need to know how to compute these things, this is the form that does that. This is a literally single variable integral, right? This is a plug and chug integral. It's already pulled back, as it were. Right? It's already on the t-axis, A to B. Crank it out. So, good for that reason. There's something nice about this form as well. Not really quite ready to talk about that yet. But what I will say already about this is there's something I don't like about this notation. And it's a gripe you've heard me make in the past. My opinion is that when you have two mathematical concepts that are different, let's not conflate them. Right? Let's not use the same word to describe two things that are, however subtly, but necessarily different. Right? So the first example we saw of this was, I don't like to conflate the word orthogonal and perpendicular. Y'all remember that? Right? They're a little bit different. Perpendicular is a geometric idea. Orthogonal is really an algebraic idea. And they correspond heavily. But they're a little bit different, and so it's good that we have two different words to describe these two different ideas. And again, let's keep the distinction. So that's what's going on here. I feel like a vector line integral is importantly different from a scalar line integral. This notation for a vector line integral makes it look a lot like a scalar line integral with a ds differential. That's potentially confusing. And so I don't like it for that reason. So most of the time I don't use this notation. There's a couple of places where I like it. We'll talk about those as they come up. Okay, let's do one. Got a curve here. Correction, we have an oriented curve here. Reminder, if you're computing a vector line integral, it's not enough to have a curve. A curve just sits there. We need an oriented curve. That orientation tells us which direction of our two options, which direction along that curve is what we're talking about as the direction we're going along the curve. So we need an oriented curve. And notice we have an oriented curve. We're told specifically that we're going counterclockwise. Is that cool? Everybody see what we got there? All right. Let's see. There's a force involved as we move along the curve. We're given the force. Okay, the wind is exerting a force of blah, blah. And the question is to compute work. Okay, fine. Well, work is a line integral. And we've already talked about how to set up work as a line integral of force over a curve. So what's the deal with that minus sign, right? And this is a tedious little annoyance. This is something y'all are probably already familiar with. At least many of y'all are familiar with. And the classic example, if I'm holding something in my hand here, there's actually two forces applying to this stylus, right? Gravity is pulling it down. I am pushing it up. Those are what we call equal and opposite. Equal magnitudes, opposite directions. They have to be opposite because the stylus is not accelerating. Right? So said differently, the two forces are negatives of each other. We need to know in this circumstance which of these two forces is relevant to what we're trying to calculate. So you just have to pay attention to the details of how things are phrased. We are told the force that the wind exerts. But we are asked to compute the work that you exert, that you perform. If you want to know the work you perform, you've got to use the force that you exert, right? And you are pushing with a force which is the opposite of the force that the wind is exerting on you. Does that make sense? Thus the minus sign in there. Everybody happy with that? Feel free to, right, we gotta make sure everybody's good with that. It's a tedious little triviality, but again, sadly, a lot of tedious little trivialities make a big difference in your answer. It may only be a minus sign, but if you're talking about, big numbers, there's a tremendous difference between big positive and big negative, right? So, trivial but important. Okay, that said, here's our integral, and this is very plug and chug. We parameterize first. Let's see here, let me not get ahead of myself. The unit circle, easy to parameterize. Notice we're only interested in the top half of the unit circle, so these values of t, not the whole unit circle, just those values of the unit circle. We take the derivative. It's very plug and chug at this point. We know that dr is r prime dt. We just computed r prime. We're given the force F. Was given as that. Don't forget this minus sign in recognition of the sort of equal and opposite and all that business, right? So the one thing that is that we need to talk about that remains is what do I do with the x and the y? And just for the change of pace, let's look at this y right here. What's the deal with that y? How do I get rid of that y? Don't forget, when you want to do the plugging in, when you're pulling back, you always pull back through the parameterization. Said differently, the parameterization, here it is. The parameterization will tell you what y is. Y is sine t. Yeah, everybody happy with that? So I like to make a big deal out of this because, believe it or not, this is a particular stumbling point that historically a lot of students have had trouble with, is remembering, hey, what on earth do I do with that? Okay. All right. So, and then you'll notice we end up with a single variable integral. It turns out to be an easy one, and we win. Okay. Does the parameterization matter? Oh my gosh, it shouldn't matter. The parameterization is some arbitrary thing that we make up to get our hands on it. It's not intrinsic to the problem. I hope the parameterization doesn't matter. Good news, it doesn't matter. Except for one thing. And that is, you do have to parameterize the correct direction. Again, we are not just parameterizing a curve. We are parameterizing an oriented curve. You've got to make the parameterization go the same direction as whatever orientation you're given. And if you go the wrong direction, then you're going backwards. And you will get a wrong answer. Does that make sense? Here's a picture. On each little piece, if you're going the wrong direction, the dr vector, if you parameterize backwards, the dr vector will be like that. Again, you'll be going backwards. You'll get the wrong answer. In fact, all of your dr vectors will be, you'll notice here, exactly the negative of what they should have been. Which means that every term in your integral, every term in the Riemann sum that you're adding up to get that integral, every single term is off by a minus sign. And the good news then is that it's not just that you'll get a wrong answer, but here is exactly how you will be wrong. You'll be wrong by exactly a minus sign. And it's very convenient to notice how you're off by exactly a minus sign. And that's all that we have here is just sort of saying that a little bit more formally. We start with a notation that a superscript means go the opposite orientation. This is opposite orientation on the same path. Same path. And the theorem just says that when you orient backwards, you will get the negative of what you should have got. that reasonable? Everybody happy with that? Okay. All right, so let's talk about how to use that fact. Real quick, let's talk about how to parameterize backwards. So we're going to look at the same example we did previously, except this time we're going to be oriented clockwise, not counterclockwise. So it's a different oriented curve. It's the same underlying curve, but with the opposite orientation. Now, if I wanted to actually parameterize like this, parameterize backwards, how do you do that? I'm going to show you two different ways to do that. On the one hand, you can just say, look, that's my parameter. That's my t. If I want to go clockwise, if I call that angle there my t equals 0 puts me here. As t increases, I'm literally going clockwise like I'm supposed to, and it ends when I get here, where that angle t would be pi. So just set up your parameter appropriately, and there's your picture. And it's just a question now of how do you actually write down the coordinates of this point in terms of t. I think the clever move on that is just to recognize that that angle must be pi minus t, but of course that is theta. Once you realize that you can solve for theta in terms of t, then check it out. Position is cosine theta comma sine theta. Right? Polar coordinates. All this in green is just polar coordinates working off of this angle theta. And angle addition formulas will allow you to rewrite like this. Ever see what happened there? There's some trig at the end here, right? So I'm using the angle addition formulas to do this last simplification here. Reminder, I do need everybody to know the angle addition formulas for sine and cosine. Very important. You'll be using it a lot in this class. Make sure you know those. Then, again, a little bit of algebra to use those angle addition formulas to get that. The other way to see this, different tool, useful in different times. The clockwise parameterization that we want. Just notice that that is the reflection. It's the reflection over the y-axis of the counterclockwise path that we already know. Sometimes you get lucky, right? This kind of thing happens sometimes. And, how do I do this reflection? What's the formula for reflecting over the y-axis? We'll take a look at the picture here. When you reflect over the y-axis, notice the y-coordinate doesn't change, and the x-coordinate just becomes the negative of what it had been. So the reflection is just putting that minus sign in the x position, and notice you get the exact same formula, exact same parameterizations we had over there. Everybody good? Okay. All right. Let me show you the best way to do this. By far the best way to answer this question. Don't parameterize at all. It says right here we're looking at the same curve. It's the same underlying curve. All we're doing is we're going in the opposite orientation. And as the theorem that we just looked at, this theorem right here, says if you're going in the opposite orientation, throw on a minus sign. It's just a minus sign. So, here we go. The curve that we're supposed to be doing, that's the same as the curve we were just looking at. Oh, gosh, excuse me. Same as the curve we were just looking at, just oriented in the opposite direction. The counterclockwise one that we already did was pi. So, opposite orientation, you get a minus sign, and thus, what we're interested in is minus pi. Much faster. We don't have to reinvent the wheel. We already did the counterclockwise. Clockwise is just going to be the negative. Is everybody happy with that? Everybody see how this is a much better way to do it? We don't have to reparameterize. We already did this work. We already did this whole calculation. Here we just acknowledge that with that minus sign. Okay, this is a good place to draw the line. I'll talk more from here on Monday. Don't forget, see y'all on Friday for the exam. See you later.
Thank you.
Yeah, sure thing.
Thank you.
Sure thing, no problem.